Okay, so I know that last section, 6.2, was a little long. 6.3 is a follow-up to that, solving trig equations part 2. So we are not, we're not heading toward new territory. We're just continuing on with our discussion from 6.2. The video for 6.2 was longish. This one we've got 2 pages of notes. We've just got 4 examples that we're going to work through. So let's take a deep breath and dive in. Remind yourself that it's usually easier, even though it arranges it like this, I really think it's easier to find that all solution statement first. And once you have that all solutions statement, then you go look at the given interval to see how many solutions fit your interval. When you have angles of rotation, you have an infinite number of solutions for each of the terminating locations on your circle. How many times are you going to use those? Okay, so example 1, we're solving an equation with a half angle. Right here in your argument, you see that we have x half. So we have in our mind half angle identities, but we're not going there. We're going to make sure that we adjust our solution statement to take that x half into account. Okay? So let's start with our equation. We're going to start with 2 cosine x half is my argument, minus square root 2 equals 0. And I need to solve for my angle. Now, when we solve, we're solving for x half, not x. We're going to move that square root 2 over to start. Finish solving for cosine of the argument. So we've got cosine x half equals square root 2 over 2. Now we cannot just multiply everything by 2. That's not going to adjust that argument here. That's not how that works. Hopefully we remember that. So my argument, my angle here is x half. So when I solve for x half, I'm going to say, okay, well, I'm looking for this angle whose cosine value is square root 2 over 2. That's what I figured out here. Cosine of x half is square root 2 over 2. That means that x half, this angle, is the angle whose cosine inverse, cosine function value, is square root 2 over 2. Well, you know where that happens, right? You know where cosine function is square root 2 over 2. Let's go ahead and look at that. Cosine is positive in quadrant 1 and quadrant 4. Cosine is positive. And we have an angle right here and right here that has a cosine function value of square root 2 over 2. Now we are in radians because we have 0 to 2 pi as our interval that was given. So right here at pi fourth, we have a cosine function value of square root 2 over 2. And right here at 7 pi fourth, down here in quadrant 4, we have a cosine function value of square root 2 over 2, right? So when I set up my all solutions statement, I'm going to say, okay, well, I've got x half as my argument. That's going to be equal to pi fourth plus 2 pi n. It is also going to be, so every time I rotate back around here, it is also going to be equal to 7 pi fourth plus 2 pi n. So every time I rotate back around here. That's my all solution statement where n is any integer. Okay, so that's lovely, but we're not done because we've solved for x half. We have not solved for x. So our last step means that we need to finish by solving for x. To solve for x, I need to multiply everything, both sides of my equation, by 2. Because 2 times x half is just x. 2 times pi fourth is 2 pi fourth, or pi half, plus, note this as well, now we have to go 4 pi n to get to the next solution. So what just happened here? Well, we just changed the period. We just stretched this function horizontally. We can no longer roll this back onto our unit circle. We start with this sketch to get us to here, but then when we solve for x instead of x half, we have applied a horizontal stretch. We can no longer map it back on a sketch. We're going algebraically. We could graph it, and we could show how that cosine wave stretches out, but we can't look at it back on the unit circle again. All right, and then right here we have 7 pi halves plus 4 pi n, still where n is any integer. So this is my all solutions statement. We were asked to find the set of solutions with, so this is B, this is my all solution statement. A is the solutions in the interval, set of solutions in the intervals 0 to 2 pi. Well, if n equals 0, so I'm not adding 4 pi, I've got pi half and I've got 7 pi halves. Well, 7 pi halves, 6 pi halves, no, let's try that again. 4 pi halves is 2 pi, right? 2 pi equals 4 pi halves. And if I'm at 7 pi halves, I'm already outside that interval. So that is outside my interval. If I go to n equals 1, I would be taking this and adding 4 pi. I'm definitely outside my interval. So I only have one solution that fits for x inside my given interval. So there's my all solution statement. There's my solution within the interval. Notice that we started with a solution for x half. That was where I started my all solution statement, but then I have to finish solving for x. So you have to take into account what your given argument is, and then make sure you go all the way to solve for that variable. Okay, let's look at number 2. What if we have multiple angles? So that was a half angle. This time we have a double angle. Well, not only do we have a double angle, but we have a double angle here, and we just have x here. We can't do that. We've got to have our argument expressed the same way on both sides of our equation. And not only do we have different arguments, we have different function values, so that's a problem. So I'm going to need to pull out my double angle identities. Let's look at cosine double angle. Cosine 2x, we've got 3 options. Which one should I choose? I've got cosine square, sine square, I've got cosine square, I've got sine square. Which one should I choose? Well, the right side is sine of x, so let's take care of both problems at the same time. We can take care of our argument matching problem, and we can take care of our trig function matching problem. If I use cosine double angle, that changes me, moves me to sine of the angle. So this is the double angle identity I'm going to use. I'm going to substitute in for cosine double angle the other side of that double angle identity, 1 minus 2 sine square x, and that is equal to sine x according to our equation. Now, my identity sheet gave my argument as a. My problem that I'm working gave my argument as x. I've got to keep it in the argument that I need. That's just my variable. It could be theta, it could be a, it could be x, it could be a half moon, it can be whatever I want it to be. But I need it to give the argument in the way that the problem expects it. All right. So I've got everything in terms of sine. I've got the arguments matching at x. I've got a squared term, so I'm anticipating that this is quadratic. I'm going to need to factor it, so I need to set it equal to 0. When I factor quadratics, I want that squared term to be positive, so let's move everything over to the right side. So I'm going to set it equal to 0. I'm going to add 2 sine squared x to both sides. Sine x is already over here positive. I need to subtract the 1. So I get everything moved to the right side of the equation. I've got it lined up in the correct order so that I can factor it like the squared function it is. Reverse FOIL. 2 sine square x is going to break down to 2 sine x times sine x. This negative 1 times 1, that's easy, but I know my signs are going to be different. Algebraic sign, 1 plus, 1 minus. I need to figure out which is which. My middle term needs to end up positive, so this 2 sine x needs to be positive. Minus 1 gives me that plus sine x in the middle. All right. Zero factor property. When I have two factors, their product is 0, I set them each equal to 0 and I solve. 2 sine x minus 1 equals 0. Sine x plus 1 equals 0. Let's see what that gives us. Well, for this first one, I add the 1 and then I divide by 2, I get sine x equals a positive 1/2. So I'm looking for the angles x where the sine function is a positive 1/2. And here for this one, I move that 1 over, I've got sine x equals negative 1. So I'm looking for the angles x whose sine function value is a negative 1. So this is my two factors solved for x, where x is the angle I'm interested in. Alright, so we're going to do sketches here. I automatically gravitate to this one because that's a quadrantal angle. That's going to be a special case. So negative 1, sine is negative 1 right here at 3 pi halves. And that's the only place on my circle that sine is a negative 1. So that is the only location there. So for all solutions, if I'm starting my all solutions statement, I've got x equals 3 pi halves, and then I've got to go a full rotation to get back there. So plus 2 pi n. And then let's look over here. Where is sine a positive 1/2? Well, sine is positive up here in quadrant 1 and quadrant 2. Sine is a 1/2 at pi 6th, and then pi 6 away from pi over here, so 5 pi 6. So those two locations. Now because sine is periodic over 2 pi, I've got to count these as two separate starting places, right? Angles, I've got an infinite set of angles that terminate here in quadrant 1. I've got an infinite set of angles that terminate here in quadrant 2. And then we've already said we've got an infinite set of angles that rotate and terminate here at this quadrantal. So let's come up here and say, okay, we've got pi 6th plus every rotation, and we've got 5 pi 6th plus every rotation, and we're going to understand that this is where n is any integer. We could also say that the n is an element of z. Z is my set of integers. So these are my all solution statements for any integer n. These are the values of x that are going to give me angles that are a solution to this equation. X is my variable. I didn't have to, this I had a half angle. I had to multiply everything by 2. We took care of our double angle here, so we didn't have to deal with it at the end. So this is my solution set for all solutions. So that's my all solution statement where n is any integer. For n is an element of the integers. N is any integers. That's my element symbol, that kind of curvy E, and then Z is my any integer symbol. Okay, what about for the interval? Well, what angles fit between 0 and 2 pi? Well, when n is 0, so I'm not actually adding the 2 pi times 0 is 0, I've got 3 pi half, I've got pi 6, and I've got 5 pi 6. Those are all between 0 and 2 pi. Now, because these are all positive values between 0 and 2 pi, if I add 2 pi to any of them, I have gone beyond that limit of my interval. So those are the only 3 solutions that fit within that interval. If I go to n equals 1 and I add 2 pi, I've moved outside my given interval. Okay, so Let's look at the next page. We've only got the 2 pages of notes in this section. We are moving right along, and I'm throwing pins on the floor. Okay, example 3. This one says I'm going to solve using a multiple angle identity. Well, why am I going to need a multiple angle identity? What do I have going on that's going to cause me a problem? I see that theta and theta, so my arguments match, but my trig functions don't. I have cosine square and I have sine square. I'm going to have to go one way or the other. But I have a handy Pythagorean identity for that, right? Sine square theta plus cosine square theta equals 1. And I've just got to pick one to change. It doesn't really matter. One thing that I notice right away is I'm in degrees because my interval is given in degrees. I am going to choose to make the substitution for cosine square theta. You just got to do one. If I substitute for cosine square theta would be 1 minus sine square theta. So there's my substitution. So my equation becomes, when I perform that substitution, my equation becomes 2 times 1 minus sine square theta. There's my substitution for cosine square theta. Minus 2 sine square theta plus 1 equals 0. So I'm going to distribute. So 2 minus 2 sine square theta minus 2 sine square theta plus 1 equals 0. I want to combine like terms. 1 and 2 is 3, and then I have a negative 4 of those sine square thetas. And I'm solving for theta, so we're just going to keep working our way through. Let's move that 3 over. So I've got negative 4 sine square theta equals negative 3, because I need to subtract the 3 to move it over. And then I'm going to divide by that coefficient negative 4. So sine square theta equals negative divided by negative is a positive. I need to solve for sine theta so that I can get theta, which means I need to take the square root of both sides. And when I take the square root, when you're solving for an unknown, you always do plus minus. All right. So I am down to sine theta equals plus or minus. Well, I can't do anything about square root 3, but square root 4 is 2. And that's a special angle value. Sine theta being square root 3 over 2, that's special angles on my unit circle. In fact, let's look at this. Sine can be positive or negative square root 3 over 2. So let's take a gander at the unit circle itself. Sine is square root 3 over 2 when I'm 60 degrees away from the x-axis. It's positive up here. Positive square root 3 over 2 at these two values. It is negative square root 3 over 2 at these two angle values. So I have 4 termination points on my circle that I'm looking at. I've got that one, 60 degrees. I've got this one, 120 degrees. Both of these angles have positive sine function values of square root 3 over 2. And then I've also got 240 and 300 degrees. These angles have negative sine function values of square root 3 over 2. Wow. Okay, so we need to find the interval. We need to find an all solution statement. So now I have a choice for my all solution statement. I know that theta is going to be the angle with the sine function value of either positive or negative square root 3 over 2, and I just figured out, you know what, I've got 4 different places where that happens. But the cool thing is, because I've got all 4, because it's positive and negative, these two are 180 degrees apart, and these two are 180 degrees apart. So instead of writing my all solution statement with 4 separate starting places, I can just narrow it down to 2. I can say, you know what? I can say theta is 60 degrees plus 180n. Instead of having to do 60 plus 360 and 240 plus 360, I can narrow that down to just 60 plus 180 plus 180 plus 180. That gets me all of those. And then I also have to say 120 plus 180n, because that gets me this set of angles as well as this set of angles, because these are opposites of each other. One has a positive square root 3 over 2, one has a negative square root 3 over 2. So there are my all solution statements where n is an element of integers. So there are all possible solutions. When I go for A, my solutions within the interval 0 to 360. Well, I see right here looking at me, I have 4 solutions where n equals 0. Whoops. Haha. Let's try that again. Where n equals 0, based on how I set this up, where n equals 0, I've got 60 degrees and I've got 120 degrees, right? Right there. 60 and 120. If n equals 1, 60 plus 180 gets me to 240, and 120 plus 180 gets me to 300. That gets me those two because of the way I wrote my statement. If I go to n equals 2, that means I'm going to take this, I'm going to add another 180. 180 plus 240 is 3 is 420, and 300 plus 180 is 480. Those are outside my interval. So I can't go that far. So my solutions in the interval are these 4 angles that show up on my unit circle. Now I didn't have to multiply by anything, divide by anything, because when I solved my equation, I was able to just solve for theta. I didn't have to make any adjustments there. All right, one more example here. We're moving right along, doing great. Again, we're solving an equation with a multiple angle. I've got cotangent and I've got cosecant. The arguments match this time. My arguments are both 2x, so I'm going to leave the argument alone. I'm not going to worry about the argument, but I do need to work in just one trig function or the other. So I am going to choose to... Cotangent and cosecant are tied together by my Pythagorean identity. I've got cotangent square x plus 1 equals cosecant squared x. So they've got this tie here, which means that if I if I set these up the right way and square them both, then I can do a substitution and get it in terms of just cotangent or just cosecant. But right now I can't do that because I've got them both on one side of the equation. So I've got to square the sides of the equation. Arithmetically, that's the way to do it. I noticed that I'm in radians for this problem. I'm going to rearrange some terms. I'm going to say, let's do cotangent of 2x minus 1 equals cosecant of 2x. So I move cosecant over to the right. I move my 1 over here to the left. Because that looks familiar. I'm liking this. And we're going to square both sides of my equation now. Now when I square this binomial, now I could have just as easily left the 1 over here and done cosecant of 2x plus 1. I don't know why I did this. It looked good at the time. You have options. Typically there's not just one way to a right answer. Now when I square this binomial, I either have to go off and FOIL off to the side or right here, or follow my pattern, square the first term. Now when I square cotangent of 2x, I'm squaring the cotangent function value, not the argument. So it's cotangent squared of 2x. Multiply them together times 2 because the outside and inside products are the same. So that gives me negative 2 cotangent of 2x, and then negative 1 times negative 1 is positive 1. That is equal to cosecant square of 2x. I'm not worried about the 2x as my argument. I just have to make sure I take care of solving for x at the end. All right, need to do a substitution so that everything matches. I've got 2 terms with cotangent. So I'm going to substitute cotangent square x plus 1 for cosecant square. Now, it's 2x, not x. That's my argument that I'm dealing with. So I've got cotangent squared of 2x minus 2 cotangent of 2x plus 1 equals substitution cotangent square 2x plus 1. My argument is 2x because that's what my argument is here. All right, let's get everything, see what we need to do to solve. First thing, I'm going to get my squared term on the same side. When I seek to do that, that adds to 0. So I'm left with negative 2 cotangent 2x plus 1 equals 1. When I subtract 1, that goes to 0. So I've got negative 2 cotangent 2x equals 0. And when I divide 0 by anything, it's just 0, right? So when I divide out that coefficient, I've got cotangent of 2x equals 0. So that's not bad. That's pretty easy. So when I'm solving for this argument, that means that I've got some angle 2x that has a cotangent function value of 0. Well, where is cotangent 0? Cotangent 0 is 0 anywhere my x-coordinate is 0. So because cotangent is x over y, so I'm looking at these quadrantals where x is 0. 0 over 1 is 0. 0 over negative 1 is 0. So when I'm looking at my circle, I've got solutions, we're in radians, so I've got solutions at pi half, where cotangent is 0, and at 3 pi half, where cotangent is 0. Do I have to write that as two separate statements? Well, no, because they are 180 or pi radians away from each other. So my all solutions statement, is going to start as pi half. So I've got 2x equals pi half plus pi n radians, where n is an element of the integers. Now what do you notice? Well, I haven't finished solving for x, right? I haven't finished solving for x. Now in the last problem where we had to make an adjustment, let's pull that over here. In the last problem where we had to make an adjustment, our argument was x half. So when we solved, we got our statement, we got it for x half. To solve for x here, we multiplied everything by 2. In this one, we've got 2x. So to solve for x, instead of multiplying everything by 2, here I need to divide everything by 2. So my statement becomes x equals, well, pi half divided by 2 is pi fourth plus pi half n. And of course, still, where n is any integer, n is an element of the integers. Now, we're not done. This is our all solution statement. We need statements within an interval. We also squared to solve. When you square to solve, you must check solutions, because I squared to solve. So I've got to stop and think, did I create extraneous solutions? So I'm going to take my values that I'm finding for my angles x, and I'm going to plug them in up here in my original equation. Alright, so in our original equation, if n equals 0, I've got pi fourth. X equals pi fourth. If n equals 0, x is just pi fourth. So let's see what happens here. Well, that would be cotangent of 2 times pi fourth minus cosecant of 2 times pi fourth should be 1. Well, cotangent 2 pi fourths is pi half, and cotangent at pi half is 0. Cosecant at pi half, well, cosecant is the reciprocal of sine, and sine is 1, so the reciprocal of 1 is just 1. So I've got 0 minus 1 equals 1. That's not true. That would be negative 1 equals 1. So this is extraneous set of solutions. That's an extraneous set of solutions. So what happens if I get around to n equals 1? Well, at n equals 1, I've got x equals pi fourth plus pi half. That would be 2 pi fourths, and 1 pi fourth is 3 pi fourths. So I've got cotangent of 2 times this is 6 pi fourths minus cosecant of 6 pi fourths equals 1. Well, 6 pi fourths lands, that's 3 pi halves. 3 pi halves, right? So 3 pi halves is down here. Cotangent is 0. That's why we picked that angle. Cosecant is -1. So cotangent there is 0 minus cosecant, which is -1, is 1. Minus the -1, that's positive. That works. That's a valid solution. That's extraneous. That's valid. Now we only have to work our way around through to 2 pi. So let's see what's next. N equals 2. Well, so I'm adding another half pi, which is 2 pi fourths. So 3 pi fourths plus 2 pi fourths would put me at 5 pi fourths. So what's happening at 5 pi fourths? Okay, 2 times 5 pi fourths is 10. So that's cotangent at 10 pi fourths minus cosecant at 10 pi fourths equals 1. Well, 10 pi fourths is 5 pi halves. Where is 5 pi halves? 1 pi half, 3 pi halves, 5 pi halves is right back up here. And we just showed that when I landed there, that was extraneous. So that's going to be extraneous again. I'm going to get 0 minus 1 equals 1, which is not true. What if n equals 3? Well, n equals 3 gets me to take this and I add another 2 pi fourths. So that'd be 7 pi fourths. X equals 7 pi fourths. And 7 pi fourths is almost all the way to 2 pi. That's my interval. My stopping place is at 2 pi. 2 pi would be the same thing as 8 pi fourths. That's 2 pi. 7 pi fourths, this is the last one I'm going to need to check. Okay, into my original equation. Cotangent of twice this would be cotangent of 14 pi fourths minus cosecant of twice that is cosecant of 14 pi fourths should be 1. Well, where is that? That simplifies to 7 pi halves. Pi half, 3 pi half, 5 pi half, 7 pi half. And when we checked this termination point before, that's the one that worked. So that is another angle that is within that interval. So these two angles work out to be solutions to my equation. These are the two angles that are in my interval. So that's my all solutions statement. Within my interval, the solutions that work are 3 pi fourths and 7 pi fourths. If I keep going, I will be outside my interval, so I don't need to check any further solutions.